All right, this is fall 2017 exam one for calculus one. For me, this is the exact halfway point because as I'm recording this, I'm planning on doing 6 total exams, and this is the start of the fourth, so I am 3 down at this point. So that's exciting for me, and it should be exciting for you because if you're going in reverse order, which means you start with the most recent ones and then work backwards, then you're also hitting exam number 3. So you are 1/3 at this point, which is fun. So let's go ahead and start with question one. Domain problem. This is the most common question one or question two you'll have, and I have not had an exam that did not have a domain problem on it. So these are good to nail down. So, with domain problems, you're just looking for the values of x that don't end up making the function undefined. So, with like a square root of x, you know that x cannot be negative. You can't take a square root of a negative number, or else you get something imaginary. So, like, with an I, and we don't want those yet. So, things like that end up causing restrictions on our domain. It looks like for this problem it looks like we've got 3 different like restrictions and worry points, which is this square root here, this square root here, and then also the entire thing as a denominator. So we have 2 square roots and we have a denominator. And I just said that when you have a square root, whatever's inside can't be negative, and also whenever you have a denominator, it can't be 0. So you just set them equal to, or not equal to 0, or greater than 0, and then get your restrictions from that. And you can do these in any order you want. I just, like to do left to right, top to bottom, kinda. So let's start with this one. We stated earlier, whatever's inside must be greater than or equal to 0. So we just set that up. X minus 1 must be greater than or equal to 0. Add 1 on both sides. X is greater than or equal to 1. So that's our first restriction. I'll write it up here in the corner. Keep track of it. Uh, for our second, let's we can either do what's inside the square root or the entire denominator. Let's do the first one. Let's do the other square root. So let's see, 2 minus x is greater than or equal to 0. Subtract 2 from both sides. Negative x is greater than or equal to negative 2. Multiply both sides by negative 1, x. Okay, this is very easy to forget. I have not had a lot of problems that cover this one little trick so far. So if you're going to remember one thing from this problem, uh, this would be very good to remember. Whenever you have an inequality like we do here with the greater than symbol, and you are multiplying both sides by a negative number like we just did, we just multiplied both sides by -1, you have to flip the inequality around. So we took this greater than and made it a less than, and that keeps it in line, the inequality. So x is less than or equal to 2. That's our second restriction we have. X is less than or equal to 2. And then for our last restriction that we saw, we have this entire denominator here. And we know that the denominator when in a fraction can't be 0 because you can't divide by 0. So square root of 2 minus x cannot be equal to 0. That is not a very good not equal sign. There we go. So to solve, we can square both sides. So then it's 2 minus x is not equal to plus or minus 0. I know that's pretty redundant to have a plus or minus 0 since they're like the same thing, but I'm going to keep it there for now, see if we need to change it later. And then, this is it's just like that. So uh, subtract 2 from both sides, so negative x is not equal to plus or minus 0 minus 2. And then multiply both sides by -1, so that's x is not equal to still plus or minus 0 plus 2. So we ended up not even needing to care about this plus or minus at all because this is still just 0 in the end, so x cannot equal 2. So that's our third restriction. So now we just take all of these restrictions that we found and put it in a form that it wants. And this, okay, this is going to get a little tricky because 4 of them are practically the same thing from 1 to 2, but they just have like different endpoints. And I guess it's a good idea to clarify what each of these mean. When you have a situation where there's a bracket, then whatever number's inside, like let's say this one, it means it includes the 1. So when you see a bracket here, it's saying, hey, it is completely legal to plug in 1, but it is not legal to plug in anything less than 1. Now, the other case is when it's parenthesis, in which case you're saying anything less than it is illegal, and 1 itself is also illegal. You cannot plug in 1. So, in situations where we have lots of uh, less than or equal to signs and greater than or equal to signs, those will usually have brackets because the equal part of it means that it can include the numbers. So, looks like here x is greater than or equal to 1. That probably has a bracket going from the right. So, looks like one of these will be our answer, not B or C, because they do not include the 1. They have a parenthesis. And then, oh, this is also a little tricky because we have a less than or equal to 2, so you'd think, oh, it's E, we got it. But we have our third restrictions where x is not equal to 2, cannot be equal to 2, so it actually would end up just being a parenthesis instead because it cannot equal 2. So looks like A is our correct answer because it starts at 1 and includes 1, ends at 2, does not include 2, which aligns with our restrictions that we had here. So that's the answer here. Okay, number 2, you have a function and you want to shift it 3 units to the left. It's one of those transformation problems where you have a graph and you're asked to like push it in a certain way or like compress it or stretch it or whatever. Uh, Fortunately, this time around we only have one transformation to worry about, which is just moving it, which is one of the easier transformations to do. So we're doing 3 units to the left, and left is horizontal, left and right are horizontal actions, moving it up and down are vertical. So whenever you are acting horizontally, whatever your function is, you always want to be acting on the x and not outside of it. So we have a horizontal function, and we are moving it to the left, so we end up doing it on the x here. So we have our 3, and then whenever you are operating on the x, you sort of flip the sign to what you think it would be. So since we are going left, and you'd think, going left, that's, negative, negativity, but we actually would end up making this positive since we are operating horizontally. And this is the correct answer. It just wants it in a different form. So let's think back to our properties of exponents. Whenever you have an exponent that has like a plus or a minus in it, it's just equal to e to the first term times e to the second term. So e to the x times e to the 3. And that ends up being our answer, C. So if you're going into this and worried that like, oh God, there's only one transformation it wants us to do here, what's the trick about it? How is it difficult to warrant there only being one transformation? Uh, don't worry, there'll usually just be something like this where you have a transformation and then simplify it a little bit, which is kind of weird, but it's good if you know how to simplify stuff. So in this case, C is the answer. All right, number 3. This is an inverse question. So you're given a function f of x, and you're asked to find its inverse and then plug x equals 5 into it. So remember for inverses, you just set it up with a y instead of an f of x. So y equals 3 plus square root of 2 plus 7x, and then end up swapping the positions of the x and the y's. So this y becomes an x, and this x becomes a y. and then you just do algebra, add, subtract, multiply, divide, get it back into a form where it's y equals, and then whatever's left is your inverse, f inverse of x. So let's go ahead and start the process of getting y by itself. I think first action is just subtracting 3 from both sides. So x minus 3 equals square root of 2 plus 7y to get this big square root by itself. And now we can square both sides to get rid of the square root. So this is now x minus 3 squared equals 2 plus 7y. I'm just going to keep this as x minus 3 squared instead of expanding it out because we are just going to end up plugging in a value. We don't have to simplify it at all. So let's just keep it like that for simplicity. Okay, and now I think we should subtract 2 from both sides. So this is x minus 3 squared minus 2 equals 7y. And now divide 7 but on both sides. So this is now x minus 3 squared minus 2 all over 7 equals y, which is what we were looking for originally, f inverse of x. And now that we have our inverse, we're just going to go and plug in the value that it asks us to evaluate it at, which is 5. So let's take this, move it up here, and plug in 5 for x. So this is now 5 minus 3 squared minus 2 all over 7. 5 minus 3 is 2 squared minus 2 all over 7. 2 squared is 4. 4 minus 2 is 2. So this is equal to 2 over 7. There we go. That is the inverse evaluated at x equals 5. All right, number 4. Express this big monster as a single logarithm, a single ln. So properties of logarithms question, yay. So we know that when you have a log of something minus a log of something else, that just equals log of on the inside, A over B. So that's how that works out. You'll see we will have to end up using that because we have a log minus another log. So we'll be using that property a little bit. Another one is when you have a log of something and there is something outside of it, that equals the log of A on the inside raised to that thing that was on the outside. So that's another one we'll be using right at the start with the 2/3 there. Let's see what else. Let's just start with those two for now and see how far that gets us. I think that those might actually be all that we need, so let's see if it'll work out for us. We always work left to right, so let's start with the one I circled here. This 2/3 can be put as the exponent out there, so ln of x plus 8 to the 2/3. You know what? So if you look at our answer choices here, there's actually there's no situation where there's something raised to the 2/3 power. So what I would like to do is just rewrite the 2/3 power as what it actually means, which is so if you have a to the 2/3, that just equals a squared and then all that cubed rooted. So let's rewrite it as that, where it is cubed rooted and then everything on the inside is squared. So that's how we can rewrite the first term here. Now we have the minus ln cubed root of x to worry about. And remember back to the first trick where if you minus two logarithms, it's just the same logarithm. It's just one logarithm where you divide both of the insides. So that becomes ln cubed root of x plus 8 squared all over cubed root of x. And since both the top and the bottom are cubed rooted, you can just take the cubed root of the whole thing. So this equals, let me make a little room here. So this just equals ln of the entire thing cubed rooted, x plus 8 squared all over x. So there we go. Last term to worry about is the minus that, And this divide by 3 is just times 1/3 ln of yada yada yada. And remember, we can just take that, treat it as an exponent. So this becomes all of this minus, that looks like a division symbol, minus ln of x squared minus 9 to the 1/3, which is the same thing as cubed rooting it. So there we go. We have a lot of cubed roots here, which is kind of a good thing. We know all of these are pretty similar. They'll probably condense up and simplify, so we sort of know we're on the right track. So we have this minus this, and we know our division trick, so this is now ln, oh, and we can use the same trick here. Since these terms are both being cubed rooted, we can just do the cubed root of the entire thing. So, well, that is not going to be enough space at all. ln cubed root of, okay, so this is x plus 8 squared all over x, and then all of this over x squared minus 9. And when you, and then, okay, so we have the original fraction, which is being divided by something else. This is the same thing as putting this bottom part in the denominator. So we rewrite this as x plus 8 squared all over x times x squared minus 9. And there we go. This is the whole thing rewritten as a single logarithm, which looks like e. I really hope that's the right answer. I'm actually going to check it because this was so long that I forget what the original answer choice was. Okay, 4e. We did it. Huh, that was a long one. Hopefully you guys will not have questions like that. This is the first time I've had that on an exam, so hopefully it won't show up. But these properties of logarithms come up in a lot of other problems, so that's probably why they asked you about it. So it's good to really know them, have them hammered down in your head. Okay, I'm going to try something a little bit different for this problem. I sort of zoomed it in a little bit so there's not as much of this gray space on the sides, because I realized that what some people do, which I want to start supporting, is they just scrub all the way to the end of the problem and then just look at the work that I did and sort of follow that. So I'm going to try to support that more and not erase a whole lot of my work. So I'm going to give myself a little more room to keep that work instead of erasing it. So number 5, this is just a limit problem. So something nice with the limits is, so usually like your x approaches the number. If you just straight up plug in that number into the equation you're given, it'll end up being undefined. Like we plug in 1 down there, this becomes 1 minus 1, which is 0, and then it ends up dividing that whole thing by 0. So that ends up becoming sort of undefined. So can't do that initially, but what you usually do, sorry, is simplify it into a different form where if you do plug in that number, it ends up working out. You just get a regular number, which will be one of these numbers. So let's try to do that. Let's try to simplify this. I think, so the top one, I actually just Googled this. Apparently it's called the sum product pattern. If you want to Google it and study it more on your own, to go ahead and simplify this, where you have, it's in the form of like that, and then it looks like we could do minus 1 minus 3. So then when you like, whoops, something's going on here. So then when you expand both of these back out, it gets you back to that. Apparently it's called the sum product pattern. And then the bottom is a difference of squares where it's x plus 1, x minus 1, where it's this number square root. And then both the top and the bottom both have this x minus 1, so we cross both of those out and we're just left with x minus 3 over x plus 1. I don't need the parentheses here. And now it's in a form where if we just plug in 1, it'll end up not being undefined. So this is 1 minus 3 over 1 plus 1, which is negative 2 over 2, which equals negative 1. That's our answer, negative 1. All right, number 6, halfway point. That's cool. Solve this, just a solve for x problem. But this looks pretty nasty. Look how many of these ln's we have here. Fortunately, the there's a lot of properties of logarithms that you can use that helps condense this down greatly, makes it a lot easier. I think the first one that we'd use is whenever you have uh, two logs that are being added. So like example here, log A plus log B, that just equals one log where they're multiplied together on the inside. So we have two examples of that. We have two logs, we have two sets, we have two pairs of logs being added together. By the way, ln is just log base e, so that's what that means. Uh, so let's go ahead and condense these. So this becomes ln of 2x plus 1 times x plus 3, all of that on the inside, equals ln of x plus 1 times 2x plus 4, also on the inside there. So now we're here. We condensed it slightly. We've only got one log on both sides, one ln. So I think now another trick we can do is, so remember that ln is just log base e. Whenever we have a log all by itself on one side, which we do, you can just treat both of these as exponents with a base that's the same as the base of the log, and then whatever you have here is what's remaining. This gets canceled out. So let's let's set that up. So we sort of do one of these where it's e to the ln of 2x plus 1 times x plus 3, and then e to the ln of all this. And then that cancels out both of these. So you're just left with, I'm going to erase that, make it clear. So we're just left with what's on the inside. Oh, I'm scrambling all my words today. 2x plus 1 times x plus 3 equals x plus 1 times 2x plus 4. Cool. Now we don't have any logs, any ln's anymore, which is awesome. This looks like just we're gonna algebra our way out of this one from here on out. So let's FOIL both of these pairs of uh, polynomials. So this is 2x squared plus 6x plus x plus 3 equals 2x squared plus 4x plus 2x plus 4. Did I get that right? 2x. Yeah. Okay, cool. Looks right. So we can combine these and these. 2x squared plus 7x plus 3 equals 2x. I don't know why. Squared, not cubed. Squared plus 6x plus 4. Okay, now let's rearrange. Let's add and subtract terms. So there's a 2x squared on both sides, so we can cross both of those out. And then let's subtract 6x from both sides. So we are left with x plus 3 equals, we subtracted 6x, equals 4. So x equals, what? Oh, nope, subtract 3 from both sides. I'm an idiot. X equals 1. There we go. I almost, I got so freaked out there because I thought it would be x equals 7, but not on here at all. So uh, hopefully that's the biggest problem you'll have with these big algebra problems. Just you can make one small little mistake and it'll feel like it all still works out, but it doesn't. So try to keep your focus. Don't get too lost track of time, and just stay focused when you're in that Elliott exam hall. I know it can be kind of hard sometimes with those 60-minute exams, but that's the best course of action, I'd say. Okay, number 7. This one's pretty fun because there's no really math involved. Just which of these statements are true about this function, or not this function, this graph uh, of a function, and yeah, it's a bunch of like continuity questions and limit questions, which are pretty fun. So let's start by going through these. A f of x, the function has a jump discontinuity at x equals 4. So let's see, x equals 4 is here. Let's make it clear. X equals 4 is here. Okay, so a jump discontinuity means that if you have a function, it suddenly stops at one point and then picks back up at a different point. That's a jump discontinuity. A regular discontinuity, a removable discontinuity, is when you have a function that stops but still continues kind of at that point. There's a hole there, but the limits on both sides both approach the same value. That's not the case with a jump discontinuity. They approach different values. So at x equals 4, what we just said here, yeah, it absolutely does. Look, it approaches there on this side and it approaches there on that side. So, yep, that is absolutely a jump discontinuity. So it is true. So we should cross it out. We're looking for one that's false. Okay, what about B? The function is continuous from the left at x equals 6. So what's x equals 6? It's this. Uh, Continuous from the left at x equals 6? Well, yeah, if you approach it from the left, it looks like it approaches the value of -4. Even if this point was not defined, even if it was a hole there, it would still be defined at that point. Since we're just finding continuity from the left, which is very rarely undefined. So we know that one is true, so it's not what we're looking for. C, f of x has a removable discontinuity at x equals -2. All right, x equals -2 is this. Removable discontinuity. Remember, okay, this is still written out on the side here. Removable discontinuity means there's a hole, but the left-sided limit and the right-sided limit still approach the same value, and that is the case here as well. As we approach the value from the right and from the left, they both approach the same value. So that one is also correct, so it's not what we're looking for. D, a little different, just the limit of as x approaches 4 exists. So limit as x approaches 4, which is here. We already actually looked at that one. Okay, I think this is our one because it's just asking for the general limit, not the left-sided limit or the right-sided limit, just the regular limit. And if the left-sided limit and the right-sided limit both are different, they both approach different values, then the regular limit doesn't exist. The limit is, it doesn't exist. It's undefined. So it looks like that one is false because we already saw that there is a jump discontinuity here from part A. So looks like D would be our answer here. Since this is a pretty abstract problem, let's do E as well and prove that we found our answer. The limit as x approaches -2 exists. Oh, that was this one that we already saw. And we know that since the left-sided limit and the right-sided limit both approach the same value, the regular limit does exist. So we know that one is true, so we're not looking for it. D is false, so it is our answer here. Okay, question 8. This is about like the 5th time I've re-recorded this problem. I can't get a good explanation quite down yet, so hopefully this is the one. If f of x here is piecewise, it's a piecewise function, which means it's defined differently for different x values. And if the function is continuous at x equals 0, then k must equal what? So so the way I want to explain this is for every single value other than x equals 0, the function is defined like this. So say the function looks like this, whatever the hell it looks like. It skips over x equals 0. So these are like the axes. At x equals 0, it's skipped over and then picks back up somewhere else. Now for when x does equal 0, it's defined by some constant k that we have to find. It could be any value of k, but we know that x must be continuous at x equals 0. So this point here must be defined basically. In order for it to be continuous here, it kind of has to continue. So must be defined there. So in order to find this value of k that when you plug in x equals 0 into the function, we need to find the limit of this as x approaches 0. So limit as x approaches 0 of x squared minus x all over 2x equals what? And that will end up finding this, like this value here, like y equals whatever. So looks like to do this we could just simplify it. Looks both the top and the bottom have a factor of x, so we can just cross all of those out. This becomes x minus 1 all over 2. We're still taking the limit. So x approaches 0, and then we can just plug in 0, and we'll no longer get something undefined. So 0 minus 1 over 2 equals negative 1/2. So that's the answer. K must equal negative 1/2 in order for f to be continuous at x equals 0. Okay, I felt like that was a good explanation. So hopefully you picked up what I just put down. So I thought that was pretty good. So question 9, just a limit problem. So first thing I always recommend doing for limit problems is just plugging in the value that you see there. So if you plug in 1 for x here, 1 for x there, this becomes, let's see, 1 minus 1 is 0, and then square root of 1 plus 8, which is 9, so that's going to be 3 minus 3, which is also 0. So this is going to end up being 0 over 0. So we know that won't really work out. If we just ended up getting a regular number like 1, 2, 3, or 4, then we would have already been done, but most of these problems aren't that simple. So we do have to put a little extra work. So now what you should do after just plugging it in is simplifying. And there's a few ways to simplify different problems. Like there should be a few different methods of simplifying in your toolkit that you apply to different problems. And this one, a dead giveaway, what we should do here is on the denominator, we have something in the form of a square root plus or minus a regular number. So when you have something like that, what you do is you multiply this entire thing by sort of this weird reciprocal thing where you copy the bottom. You mostly copy the bottom. We're going to rewrite both of these parts and then flip the sign. So we're going to multiply this by square root of x squared plus 8 plus 3. And then same thing on the numerator, so it's all like balanced out and everything. We're not really changing the problem since this will just evaluate to 1 here. And then we do and multiply that, and then what we get afterwards, we will not have any on the denominator. There won't be any like square roots or anything, so it'll be easier to simplify from there. So let's go ahead and multiply this out. I'll start with the top, which I'll just keep as, multiplying both of these parentheses together. If we actually went and FOILed all of this out, then that would get extremely messy with a bunch of square roots and yada yada. So let's go ahead and not do that. Let's keep it as this for now. And it should be fine since it's just in the numerator. Usually you're just trying to simplify the denominator in these problems. So when you go ahead and simplify the denominator, it's first term minus that term, which is just x squared plus 8, and then it's minus, and then it's square root of x squared plus 8 plus 3, square root of x plus 8, x plus 8 minus 3. So that ends up not really doing anything since we're just going to plus and then minus the same thing. So don't need to do that. And then negative 3 times positive 3 is, whoops, what's going on? Negative 3 times positive 3 is negative 9. So it's x squared plus 8 minus 9 on the denominator. And now let's go ahead and simplify this a little more. Plus 8 minus 9 is just x squared minus 1, all under all of that. And this now is a difference of squares, and we know how to simplify those. That is just the first times that, so x plus 1 and x minus 1. So when you end up multiplying these back together, you'll get back to that, which is pretty cool. And let's rewrite the top now that we're pretty far down, not lose track of where we got from. Plus 3 Cool. Now, okay, cool. So now you'll see we have an x minus 1 on both the top and the bottom. So we can go in and cancel both of those, and we're left with x squared plus 8 plus 3 all over x plus 1. And now you'll see if we end up plugging in that value again of x approaches 1, the denominator won't equal 0 anymore. So this will probably just work out to a regular number, and we'll have our answer once we plug it in. So let's go ahead and plug in 1 here. So this will be 1 squared plus 8 is square root of 9 plus 3 all over 1 plus 1, which is 2, which equals square root of 3 plus 3 is 6 over 2, which equals 3. There we go. Answer choice C. So the big trick with this problem is recognizing the denominator has this square root plus or minus a real number. When you have that, it's most of the time you'll end up having to do this multiply by this reciprocal thing here, and that'll usually simplify out, and you'll get your answer that way. Cool. So question 10, the line y equals 3 is the left horizontal asymptote of which of the following functions? So this is like the reverse of a problem that I'll usually ask you, where it's like find the asymptote of this function, like find the equation of the asymptote of a given function, but it's asking you to go in reverse. So here's an asymptote. Which one of these functions has that asymptote? So let's visualize that a little bit. If we have a graph here, and okay, so the line y equals 3, that looks like this, where at, oh, no, that should be negative. Y equals negative 3, there's a line, which is our asymptote, so let's actually make that dashed, so it's clear that's an asymptote. And then for some function here, when you draw it out, it'll end up on the left, it'll kind of approach it, going like that. It'll go off to infinity, but it'll sort of rest on this asymptote. So which one of these functions works? There's a really easy way to determine that, and it's just for each one of these functions, plug in a really, really small or really big negative number. So like, let's say for the first one, y equals negative 3 times e to the x, just plug in like negative 1,000 for x, and then whichever one of these functions yields a number close to negative 3 is your answer. So let's do that. So let's start off with the first one. Y equals negative 3 times e to the x, so negative 3 times e to the negative 1,000. So as the okay, so this is a e to the negative number, which just equals negative 3 times e to the positive 1,000 on the bottom, and and that'll be basically 0, right? Because e to the 1,000 is a massive number. Uh, it's exponent like that, it's ginormous, and when you do negative 3 divided by a massive number, that's just very close to 0. So we know that one is wrong. It's not really close to negative 3 at all. So let's try B. 1 over negative 1,000 plus 3. So 1 over negative 1,000 plus 3. That is 1 over negative 997, which is also not really close to 3. That's pretty close to 0. So that one's also, we know that one isn't really true. C, y equals negative 3 times negative 1,000 all over 1 plus negative 1,000 squared. So this is 3,000 over 1 plus a million. So a million and 1. There we go. Put some commas in there. Yeah, that is also not really close to negative 3. That's pretty close to 0 as well. Because if we do something, instead of negative 1,000, we do something like negative a million or negative a billion or whatever, we know this squared here is just going to keep growing faster than what's up here, so it'll approach 0 instead. So that's what this means on the right. What it approaches, like a limit. Probably should be using limits for this problem, but you can brute force it if you want. Okay, D. Hopefully this is a 1 in 2 chance. So 12 times negative 1,000 squared minus, or plus 1,000. All over 1 plus 4 times negative 1,000 squared. Okay. Well, both the top and the bottom both have a squared term, so this does have a chance of actually approaching a regular number instead of 0. So let's see, 12 times, so that's 12 million plus 1,000. Okay, a million is way more than 1,000. We can basically just ignore that plus 1,000 on the top there. And then same thing with this 1 plus down here. That's really just going to be a fart in the wind compared to this million right here. So it's 4 million. And this one equals 3. Oh, really close here. This is positive 3 instead of negative 3. So we know. So this is what basically a clue to what answer you'll end up finding. If it wants to approach like an actual number instead of 0 or like infinity or something, then both the top and the bottom they'll have the same like order. So it'll this order of this is 2, order of that is also 2. It won't be something like what we've done where the order of this is 1, order of that is 2, and they're different. So that one will usually approach 0, but something like D probably approach a non-zero number, which is cool. But it's not negative 3, so we know D is false. Let's go ahead and verify that E is the correct answer since there's a lot of work involved in these. So e to the negative 1,000 minus 3 all over e to the negative 1,000 plus 1. Okay, so well, okay, when you have an exponent raised to a smaller and smaller negative number, that approaches 0, so we can ignore both of these. So this ends up becoming negative 3 over 1, which equals negative 3. So yeah, E is our correct answer here. I suppose if you actually wanted to calculate this, it would probably involve limits. Just sort of like in the reverse, I guess. You could take the limit as x approaches negative infinity for each of these if you wanted. But to actually like, I actually don't really know how you just do like a general example and then end up with an answer that's, A, B, C, D, or E. The only two ways are through a limit or plugging in actual values for each of these and brute forcing it. So really wish I could help you out there, but this is the easiest way I could find to do one of these problems. Just brute force it, plug in a bunch of really small numbers. All right, question 11. We're almost done here. Let's go. If the tangent line to the graph of whatever that is, doesn't really give us the function, at x equals 4 goes through these 2 points here, 5, 3, and 7, 7, then what is f of x at 4? Or f of x at x equals 4? Okay, that is a big mouthful. So let's understand what it's asking. So we have some function. We don't know what the hell it looks like. It could be that for all I care. And let's see, we have our axes. So at x equals 4, so let's say right here where it's 4, there's a tangent line. So it's derivative basically. And we draw that big line out. It passes through 2 specific points, 5, 3, and 7, 7. And if we have that line, then we're asked to find what the actual value is right there at x equals 4. So that's our unknown. We're trying to find out what this value is here. So, well, what I think you should do is, well, we're given that this tangent line here, it passes through these 2 points. So what we could do is, since we have those 2 points, we can find out what the equation of the tangent line is. And then when we have that, we can just plug in x equals 4 into that equation. And then what we're left with will be our answer of what the actual function's x equals 4 value is. So let's go ahead and try that. So I know I'm not really supposed to erase anything here, but that was just way too damn big. I should probably, let's do a smaller example over here. We have x equals 4. I have our function, which is that tangent line, our 2 points. We'll say it's A and B, and then our value here and what it actually equals. Cool. So we have our 2 points. How do we find the equation of a line that passes through 2 points? So it's a two-parter. First part is we find the slope of that equation based on these 2 points, which is just, so if we have, let me write this a little bit bigger, 5, 3, and 7, 7. This is x1, y1, and x2, y2. We do this equation, which is y2 minus y1 over x2 minus x1. That'll be our slope. So this is 7 minus 3 over 7 minus 5, which equals 4 over 2, which is 2. Cool, so now we have our slope. And then using that slope, we can use the point slope form, which is y minus y1 equals m, the slope, times x minus x1. This y and x aren't actually values. You just use literal x and y for that. So I'll show you what I mean. We'll do y minus y1, which is 3, equals our slope, which is 2, times x minus x1, which is 5. So this is y equals 2x minus 10 plus 3, which is minus 7. So this here is the equation of this tangent line that we stated earlier. And now all we have to do is plug in x equals 4 for x here. So let's put it up here. Y equals 2, oops, y equals 2 times 4 minus 7. Y equals 8 minus 7, which equals 1. There we go, D. So that's how you'd find this weird specific set of pieces of information of how you get the f of 4 of this function that we don't even know of. Question 12. We have made it at the end of this entire exam. What's it? Fall 2017, so 6 years ago, time of the recording. That's man, I just started high school when I was doing that. Anyways, the graph of f prime, which is the derivative of f, is shown below, which is this. What does the original graph of f look like? Why did they use 2 question marks? That's like what you do on the internet. Anyways, all right. So basic properties of derivatives and what their graphs look like. If you have f prime and it's positive here, then that means the graph of f, whatever it looks like, we have our axes here. That means that for this segment here, let's go ahead and like put those 2 lines here as well. It will be increasing for everything here. It'll only be going up. And then at this specific point here, when it changes from positive to negative on the bottom, then it will start decreasing like that. And at this point, it'll be like a little hump, and it'll equal, its derivative will equal 0. What is going on? My glove is acting up. And then the opposite for this bottom part here will be decreasing until it hits the second part there, until it levels out, and the derivative will equal 0 at that point. So let's go ahead and translate everything I just said to A, B, C, D, or E. We can immediately rule out A because it has this weird spike, And whenever you have a spike like that, it means its derivative at that point is there's a discontinuity. So its graph of f prime will look like graph will go like that. Stop, jump back somewhere else. And we know that doesn't look like that at all. So we can disregard A for this one. Um, okay, so what about B? This one also is not true because if you look, it uh, its derivative changes from positive to negative back to positive. So, and I'll segment them a little bit. 1, 2, and 3. So segment 1, it's increasing. Segment 2, it's decreasing. Segment 3, it's increasing. In order for that to be the case, then in our original f prime, it would have 3 segments as well, but this one only has 2, 1 and 2. So this part is positive and this part is negative. So we know that. Whoa, I should not have circled A. Hopefully you guys didn't pick that up. No, it's not A or B. Okay, so what about C? Well, it's 2 segmented, right? It's got 1 and 2, and the point where it ends at, its derivative, it looks like it equals 0, right? It's kind of like forming a little bowl, you can see. And that is exactly the case because if we look back at f prime, it ends at 0. It ends back on the axis, the x-axis. So that looks good. What about yeah, actually, there's not really anything else to look about it. It looks very correct. So I'm gonna underline C because I think that's gonna be right. But this is a very abstract problem. There's not really any calculation where you know for sure it's the right answer. So I'm going to go ahead and look at D and E first, cross them out, and I'll come back and circle C. So what about D? So this is a good thing. It's like 2 segmented. Which follows f prime, but it's in the opposite order. So we can see in segment 1 it's decreasing, and in segment 2 it's increasing. This is opposite from what f prime is, where it goes from positive, increasing, to negative, decreasing. So D goes from decreasing to increasing. F prime tells it that it should go from increasing to decreasing. So we know D is wrong. E looks like that fixes the mistake. Whoops. It goes from increasing to decreasing, but it is wrong in the sense that where it ends is not a derivative of 0, where it's flat. It does not form like a bowl like we saw with C. So it just, it kind of looks like it just want to keeps going down. So that contradicts what we saw earlier right here, where it's supposed to end at the origin and it's supposed to form a little bowl. So we know that E is also wrong. C was our correct answer originally. It's just nice to go ahead and cross everything else off so you know you've got the right answer. So, hooray! We just did an entire exam. Look at all this nice work. I like to use this cyan color. A lot of people like to use this regular blue that's boring and not cool. It's plenty cool. I'm just playing. But yeah, one whole exam done. I think I'm 4 in at this point, which is cool.